Hello everyone and welcome back to another lecture of Power System 2 bearing AKTU code as KEE601. My name is Kitty Tripathi and I am faculty of Electrical Engineering Department in Babu Banarsi Das Northern India Institute of Technology, Lucknow. So, in today's lecture we will be starting module number 3 of this syllabus of Power Systems 2, which is travelling waves in power system. So, let us begin. But before beginning, let us understand what are the outcomes after we have studied this module 3. So, let us understand the course outcome before starting and what are the prerequisites which are required to study this module. So, first things first, what are we going to get or what we will be able to understand when we have completed this module? First thing is, the most important thing which we will be able to do after this studying of this module is, we will be able to understand what are the travelling waves and how is it behaving differently in different kinds of situations in the transmission lines, like when it is an open circuited line, when it is terminated line with a particular impedance, or it is a short circuited line, whether it be a long transmission cable. So, what are the things which we will be able to do when a wave is travelling? We will get to know all the terms and terminologies and the behavior as well. Not only this, we will also in this module study about the reflection and refraction in the T section of the transmission line. We will also understand what is attenuation in the travelling wave and how it is annotated. And lastly, we will be studying about Bewley lattice diagram, which is a very interesting concept and we will see to it when we come to this part. Okay. What are the prerequisites which are required to study this module? So, the primarily prerequisite is power system 1, which we have studied in the previous semester. Along with it, electromagnetic field theory, some of the basics which you have already covered in electromagnetic field theory of the travelling wave, where we have studied already how electromagnetic waves travel in a transmission line. So, some of the fundamentals which we have already studied in this subject will be needed here. So, let us first begin. So, to begin with, how do we represent a transmission line and why are we studying this? Let us make a quick overview on this. So, first things, what do we say a transmission line is? We say there is a transmission line, it is used for transmission of power. From where? Electrical power is transmitted from the generating station to the distribution unit, as simple as that. It is used to where the power is being generated, connected to a substation, and from that substation it is distributed to various number of kind of users, whatever the person may be, right. So, this is the entire process and these transmission is done through the set of lines called as transmission lines. Now, what happens in this transmission line? We have the waves of voltage and current which is being transmitted from one end of the line to the another end of the line. So, if we very simply if we say that we can consider two wire system and simply represented this two wire system as a transmission line, then what are we trying to say? We are simply saying कि if हमारे पास parallel wires ऐसे connected है जिनको हम transmission line की तरह बड़ा simple annotation हम ऐसे ही indicate करते हैं. So, if there is the most simplest annotation of this power system module, then we say that what is happening, from one end of the cable to another power is being transmitted. This from where it is transmitted is a generator end, where the power is being generated by the generator and then it is being transmitted to particular user. So, this is load side. Okay. So, this is very simple. What is happening here? These parallel lines are being fed by some AC power generated through a generator. So, see here in this diagram we have annotated, if you have remembered the module number 1 of this subject specifically, we represent this as a per unit representation of any generator module. So, this is what is being indicated here. So, we have indicated that generator module as Vs and its per unit impedance as Zs. Now, the transmission line is there, we have transmitted and at the end of the load it is there is some kind of load which is receiving this power which is being sent from the generator end, right. This is the simplest representation. Now, let us quickly understand one more thing, which is how the transmission line is being represented. So we have already studied in power system 1 that a transmission line can be annotated with the help of 4 parameters. What are those 4 parameters? Resistance, inductance, conductance and capacitance. ये ही 4 composed हैं जिनसे transmission line indicate की जाती है. पूरा impedance of the transmission line is entirely indicated through these 4 parameters only. ठीक है. अगर हम यहाँ पर मान के चल रहे हैं कि हमारे पास कोई शॉर्ट एलिमेंट यानी शॉर्ट ट्रांसमिशन लाइन है, तो व्हाट डू वी से? इवन वी हैव स्टडीड शॉर्ट, मीडियम, लॉन्ग. व्हाट आर वी ट्राइंग टू से अबाउट दिस कंपोनेंट? कि यहाँ पर ये क्या है? ये डिस्ट्रीब्यूटेड पैरामीटर्स हैं. तो व्हाट इज द प्रॉपर्टी ऑफ द डिस्ट्रीब्यूटेड पैरामीटर? कि दे आर बीन डिस्ट्रीब्यूटेड ओवर लेंथ. So this resistance, inductance, conductance, capacitance, whatever we are trying to say, this is what it is indicated or with respect to length. So we normally use it per unit length. Okay, that is what we have written it here. Ki we use inductance per unit length, capacitance per unit length. What about R and G? They are the lossy component, right? Resistance is known to be lossy component. And G is what? 1 upon R, which is conductance. So this is also the lossy component. So if we are not considering lossy component, then the transmission line consists of only L and C. When we consider the transmission line, the losses also, then we consider it through all these 4 parameters R, L, G, C. ठीक है. लेकिन ये याद रखना है कि जब भी हम ये चारों पैरामीटर्स को यहाँ इंडिकेट करेंगे, we will be indicating such that कि ये चारों पैरामीटर्स क्या हों? पर यूनिट लेंथ में रिप्रेजेंटेड हूँ. Why? Because they are distributed parameter, we cannot take that for granted. Now, inductance में what do we say about inductance या property of inductance? That the flowing current give rise to the combination of inductance per unit length. It is between the series element, what we can say. हम जब भी इंडक्टेंस को इंडिकेट कर रहे हैं, हम सीरीज ब्रांच ऑफ ट्रांसमिशन लाइंस में रिप्रेजेंट कर रहे हैं. ठीक है. सिमिलरली जब भी हम कैपेसिटेंसेस को इंडिकेट कर रहे हैं, हम शंट ब्रांच में इंडिकेट कर रहे हैं. वी हैव ऑलरेडी स्टडीड दीज थिंग्स इन पावर सिस्टम 1. जस्ट अ क्विक रिकैप आई एम डूइंग हियर, राइट? सो दिस इज व्हाट वी हैव ऑलरेडी स्टडीड. एंड टू बी नोटेड दैट दीज टर्म्स आर टू बी यूज्ड इन पर यूनिट लेंथ, राइट? सो दैट we can consider the parameter as per the distributed parameters logic and we are not considering them as lumped. That is why if we have to consider this at lump, we have to take it per unit length and for a particular instant we are solving, and that is what we are going to do in this entire unit. So let us understand this through a diagram what I was trying to say. See here, the first figure here shows 2 parallel lines. This is the general indication of a diagrammatic pictorial representation of transmission line. ठीक है. Sending end पर क्या है? Voltage as a function of distance. Now if you remember previously when you have studied electromagnetic waves and the travel, we say that if electric field and magnetic field are in x and y direction, that the traveling of the electromagnetic waves moves in the z direction. So using that simplified logic there only, we have represented voltage and current as a function of distance, indicating as from z. ठीक है. And it is also a function of time, so it has been written as t, z comma t. So the voltage and current as a function of distance and time. So this is the indication of transmission lines. Here it is sending end. ठीक है. Here it is receiving end. So from sending end and receiving end, there is a length of transmission line. The parameters are distributed. What are the 4 parameters? Distributed resistance, distributed inductance, distributed capacitance and distributed conductance. Now how do we denote them? So first things first, resistances and inductance are to be considered in the series branch, and conductance and capacitance are to be connected in the shunt branch. जब भी हम रेजिस्टेंसेस को कनेक्ट कर रहे हैं हमें ध्यान रखना है कि एक लॉसी कंपोनेंट है, ये पावर डेसिपेट करता है, और क्योंकि ट्रांसमिशन लाइन की लेंथ ज़्यादा है, नॉर्मली हम पर यूनिट लेंथ में हम नॉर्मली इसको किलोमीटर्स में रेफर करते हैं, सो इट इज़ बीन रिप्रेजेंटेड एज ओम पर किलोमीटर. सिमिलरली व्हाट अबाउट डिस्ट्रीब्यूटेड इंडक्टेंस? इंडक्टेंस के लिए क्या बोलते हैं? इट इज स्टोरिंग एनर्जी. विच टाइप ऑफ एनर्जी? इलेक्ट्रोमैग्नेटिक एनर्जी. सो इलेक्ट्रोमैग्नेटिक एनर्जी जितनी स्टोर हो रही है इस ट्रैवलिंग वेव में, that's the storage property is being done by inductance. That is what we have studied about inductance since childhood. So here also we are taking this with respect to the distance, and since it is a long distance we generally consider it with kilometer. So here also we are representing inductance by Henry per kilometer. Similarly goes with the conductance and capacitance, but the thing is we represent them in shunt branches. Conductance में what we are basically saying is again the kind of losses. So it basically models dielectric losses, ठीक है, ohm inverse per kilometer or which is Siemens per kilometer. Similarly for capacitance, when we are saying capacitance is again what? Storage, energy storing device. It stores energy. Which kind of energy? Electrostatic energy. So the due to the electric presence of electric field, the energy stored is in the terms of capacitance, denoted in the shunt branch, and since it is a distributed parameter, it is again taken per unit length. Since it is a transmission line, so distribution of length will be in kilometers only, so the unit goes as farad per kilometer. Okay. And what about the representation? See here. So what we have represented here, in the series branch we are representing resistance and inductance. In the shunt branch we are indicating conductance and capacitance. Alright. What we have introduced separately is delta x, delta z. Delta z indicates the distances. The delta z distance has been travelled, then the resistance is r into delta z because of the resistance distributed constraint of the parameter. Similar goes with inductance, it is L into delta z. Similar goes with inductance and similar goes with capacitance, since all the four terms are distributed parameters, right. So delta z is indicating distances, okay, the distance, amount of distance it is been travelling. What else we have visible through this figure? That initially at the sending end we have current I and V, which is a function of distance z and time t. If it has travelled a particular distance delta z, then the resistance will be R into delta z. Similarly, inductance L into delta z, conductance G into delta z, and capacitance C into delta z. So here what has happened? Delta z distance has been already travelled. So what is remaining after it? The current will now be a function of not z, but we can write it as z plus delta z. So see here, current has been indicated as z plus delta z. Similarly, voltage here is indicated as z plus delta z, just showing that a delta z distance has been travelled in this transmission line. This is how we represent, and this is how we are going to use it for the study. But before we study, let us consider one more thing, which is the most important case, that is normally which we use for calculations is ideal or lossless cases. So what about ideal and lossless cases? If we say that the transmission line is lossless, then what do we mean? Ki the lossy components will not be there. What are the four components? Inductance, resistance, conductance and capacitance. See, inductance and capacitance are energy storing device. बच क्या गया? Resistance and conductance. यही हैं जो लॉसी पैरामीटर हैं, वैसे भी resistances को लॉसी पैरामीटर बोलते हैं. So these are the lossy parameters. ठीक है. अब अगर हम कह रहे हैं लॉसलेस या आइडियल है तो क्या है? लॉस जीरो है. लॉस जीरो है तो these parameter do not exist. Then what happen? R is equal to G is equal to 0. So what will be the transmission line diagram what we have just represented modified into? Here see, we do not have now R, here also we do not have any G. What only remains is the combination of inductance and capacitances. Again here we are showing that we have travelled a small distance dx. So the inductance is going to be L into dx and capacitance is going to be C into dx, and the travelled value is changing with respect to delta x. Since it is a rate of change, That is why we have written rate of change of current with partial differentiation with respect to delta x. Similar goes with the voltage, partial differentiation with respect to delta x again, and delta x is a distance which we have already travelled in the transmission line. Okay. Now, let us quickly understand how we indicate this through an equation. So, what we can say, even if we consider R into delta x and inductance L into delta x, similarly here we can say G into delta x and here it is capacitance C into delta x. ठीक है. Here we have V and I. यहाँ V फंक्शन हो जा रहा है x प्लस डेल्टा x डिस्टेंसेस का और करंट भी फंक्शन हो रहा है x प्लस डेल्टा x एंड द टाइम इज ऑलवेज द फंक्शन. ठीक है. Now what do we want to write? We want to write equations. How are we writing? So simply we write, if you want to say that the receiving end, what we can see here, if we simply indicate through what you call as KVL, how can we simply apply what? Net voltage in the cycle. Net voltage will be equal to the voltage sending end plus the potential drop here and here, right? We can simply write it as, so we are simply doing what? We are writing voltage at x plus delta x, which could only be represented as voltage at x plus voltage drop at resistance, which is R into delta x into I. Current is again a function of x and t also. ठीक है. Similarly, L into delta x indicates an inductance. Now, inductance में voltage can be written as L di by dt. So, it is di upon dt. This I is again a function of x and t. ठीक है. Now, if we write it as Vx plus delta x minus V of x delta x I x comma t plus L delta x di by dt. ठीक है. Similarly, we can write the equations for the current using KCL, right? So, we have written the equations for voltages and current. What we will get to know is, we can write it as del V by del Z. What are we doing? Simply change in voltage को हम differentiate कर रहे हैं with respect to distance now. Del V by del Z. ठीक है. इस साइड करेंगे तो क्या होगा? अगर हम R into, we are taking it equal to, then it is plus only. R into C, we are writing it rate of change with respect to distance. Z, or we can write it as this x. If we are taking it, because we have initially indicated Z and delta Z, that is why I have written here Z, it can be x also. There is no issue about x and Z here, right? This, all the terminologies what we are writing it is only indicating distances. Now what are we trying to say कि अगर हमने differentiate किया है with respect to distance, so see here R into delta x differentiation हो गया है with respect to distance, it only gives as a function of I only, because x distance का differentiation with respect to distance is going to be 1, so it becomes R into I. ठीक है. Minus of R into I minus L di by dt. See here it was minus here because it is potential drop, it is minus here because it is potential drop. ठीक है. Minus L di by dt was already written. We simply write it as L di by dt. What about delta x here? Since we are differentiating with respect to time, it is again going to be 1. So, the equation converts to something like this. Similarly, if we write the KCL equation for these shunt branches, we can write it as delta I by delta Z. ये current को differentiate कर रहे हैं अब distances के respect में. We can write it as minus G into, Now conductance can be written, current can be written as conductance into voltage. तो G इंटू डेल्टा एक्स था, अब डेल्टा एक्स यानी डिस्टेंस का डिफरेंशिएशन, फिर डिस्टेंस के रिस्पेक्ट में 1 हुआ, केवल बचेगा क्या, G इंटू वी वोल्टेज ओनली. एंड द अदर टर्म वॉज कैपेसिटेंस. कैपेसिटेंस को भी हम अगर करंट की कैपेसिटेंस लिखी जाए तो C dV by dt होती है. सो इट विल बी C dV by dt. अगेन इट वॉज C इंटू डेल्टा एक्स, सी हियर डिस्टेंस. अब हम क्योंकि डेल्टा z डिस्टेंस के रिस्पेक्ट में ही डिफरेंशिएट करें, इट इज अगेन गोइंग टू बी 1. द इक्वेशन बिकम समथिंग लाइक दिस. ठीक है, इट इज वेरी सिंपल to understand this equation. What are we now trying to do? We are now trying to do is differentiate. We can see here what we have reduced, and we can directly differentiate and substitute it in the other one also. So, see here we can differentiate the equation number 1 which we have written above with again with respect to distance only. It will be double differentiation. What we can write, del 2 V by del Z square is equal to, now it is minus of R into, now current is also getting differentiated with respect to del Z. So, we can write it as minus of R into del I by del Z, because we are differentiating again, second time differentiation. So, R is a constant, only differentiation can be the changing quantity which is current here. Similarly, when we write it here, we can write as minus del, it is already differentiation with respect to time once, and we are now differentiating it with respect to distance. So, we can write del by del t into del z, del 2I. The equation number 1, ठीक है. Similarly, we can write for equation number 2 also. Now, see here, del I by del z. Can we substitute this value here? Yes, of course we can. Let me have a fresh blank canvas for writing it. Now, del 2 V by del Z square. What it was? Minus of R into differentiation of current with respect to distance. What we have obtained here was, we can substitute from the previous equation, which will become minus G into V minus C into dV by dt. ठीक है. What was the second term which was there? Minus L di by dt into di by dz. So, minus L del upon del t into del z of I. I के लिए फिर से हम ये minus GV into C dV by dt लिख सकते हैं. So, it will be minus GV minus C dV by dt. Now, what? We can rearrange it. What we can and simplify, and what we can write, d2v by del z square is equal to, we will be getting it as minus R di by dt. See, now what we are doing is minus L del by del z of del upon del t of I. This is what we have simplified. Without substitution, this is what we have obtained. Now, what we want to do is, let us write an equation, del V by del X, ठीक है, change of voltage with respect to distance into dx. What it can be written as? Minus, if we are not considering the distances and ignore it, what we can write as, why we will not? Because again it will be the constant and it becomes to 0 only. Any which ways it is going to be 0. So, no issues, minus L dx into di by dt. And what can we similarly write for the current equations? So, del I by del x into dx can be written as minus L d2I by minus C d2V by dt into dx. So, what are we trying to do? We एक बार हम जो KVL की इक्वेशन है उसमें डिफरेंशिएट करेंगे विथ रिस्पेक्ट टू डिस्टेंस, और KCL की इक्वेशन है जिसमें डिफरेंशिएट कर देंगे विथ रिस्पेक्ट टू टाइम. वी विल गेट वन कॉमन क्वांटिटी. सी हियर दिस वन, अगर इसको हम डिफरेंशिएट कर दें, देखो यहाँ पर केवल dt के साथ डिफरेंशिएट कर दें इस इक्वेशन को, तो these two term will become same, and we can correlate those two terms and can simply obtain the representation. What will be the simply obtained representations? That will simply be represented in the terms of del 2 V by del t into del x, both side it is there, ठीक है, into c can be written as del 2 I upon del t square del x. अब हम यहाँ पर बेसिकली करना क्या चाह रहे हैं, जो ये वाला टर्म KVL वाली इक्वेशन में डिफ्रेंशिएट करके था उसको सब्स्टिट्यूट कर दे रहे हैं KCL वाली इक्वेशन में, एंड वी कैन ईजिली गेट द इक्वेशन ओनली विद द वोल्टेज एंड ओनली विद द करंट. दैट इज व्हाट वी आर ट्राइंग टू रिप्रेजेंट कि वोल्टेज का डिफरेंशिएशन इंडिकेट कर रहा है वेव के प्रोपोगेशन को विथ रेस्पेक्ट टू द डिस्टेंस. सिमिलरली करंट का डिफरेंशिएशन इंडिकेट कर रहा है प्रोपोगेशन ऑफ द करंट विथ रेस्पेक्ट टू डिस्टेंस. सो वी कैन राइट द wave equations in the form of voltage equations and well as current equations. Here it will be only a function of voltage, distances and time. Here it will be only as in functions of current with distance and time. No usage of voltage here, no usage of current here. We can annotate the wave equations for voltage and annotate the wave equations for current likely. That is it for this lecture. The other terminologies we will be studying in the upcoming lecture. Thank you.